Imagine the universe as a grand, intricate clock, with the standard model of particle physics as its manual. But what if one tiny gear doesn't behave as predicted? The muon, a subatomic particle, shows a strange wobble that's shaking physics. The Muon-g2 experiment found this anomaly, hinting the standard model is missing something big. It could point to new particles, forces, or even hidden dimensions. The universe is whispering a secret, and physicists are listening closely. The Moon is like the electron's heavier, more unstable cousin, about 200 times more massive. This extra heft makes it a sensitive probe for new physics. Place a moon in a magnetic field and it spins and wobbles like a tiny top. The speed of this wobble is set by its magnetic moment, or G factor. In a simple world, the G factor would be exactly 2. But quantum mechanics complicates things. The vacuum is a frothing sea of virtual particles, subtly altering the muon's properties. The standard model predicts this deviation, called the G2 anomaly, with incredible precision. The Muon-g2 experiment aims to measure this value just as precisely. If experiment and theory match, the standard model stands strong. But if there's a difference, it means something new is at play. Unknown particles or forces nudging the muon. And that's exactly what the experiment has found. The muon's wobble is a signpost pointing beyond the known. The standard model has been our guide to the subatomic world for 50 years. It organizes matter into quarks and leptons and explains 3 of the 4 fundamental forces. Its predictions have been confirmed to astonishing accuracy, making it the most rigorously tested theory in science. But it's incomplete. It leaves out gravity, dark matter, and dark energy, together 95% of the universe. The standard model describes only the visible tip of the cosmic iceberg. We know there must be physics beyond it, but until now, we've lacked direct evidence. The Muon-g2 anomaly could be the first real clue. A flicker of light in the darkness. It's a sign that our map of reality is missing entire continents. The search for what lies beyond has just begun. At Fermilab, the Muon-g2 experiment uses a massive magnetic ring to measure the muon's wobble with mind-boggling precision. After years of data, the results are clear. The muon's G2 value is slightly larger than predicted. This tiny difference, measured in parts per billion, is hugely significant. The combined results from Fermilab and Brookhaven have now crossed the 5 sigma threshold, the gold standard for discovery in physics. This isn't a fluke, it's a real persistent crack in the standard model. For decades, the standard model has withstood every test. Now the muon's extra wobble is a direct sign of something new. It's the first solid evidence for physics beyond the standard model in a generation. The question is no longer if new physics exists, but what it is. The anomaly is our guide, leading us into unexplored territory. Physicists are now racing to explain what's causing this mysterious effect. The muon's wobble is a cosmic breadcrumb, pointing the way forward. The hunt for new physics is on. What could be causing the muon's extra wobble? One leading idea is supersymmetry, or SUSY. SUSY predicts every known particle has a heavier superpartner, which could influence the muon's G factor. If these particles exist, they'd pop in and out of the quantum foam, nudging the muon just enough to explain the anomaly. Other suspects include new heavy force carriers, like a Z' or W' boson, or even exotic leptoquarks that blur the lines between matter's building blocks. Each of these possibilities would revolutionize our understanding of the universe. The Muon-g2 anomaly could be the first indirect evidence for a fifth force or a new family of particles. Theoretical physicists are now racing to see which idea fits the data best. The mystery is wide open. The Muon-g2 anomaly might even connect to one of the universe's biggest mysteries, dark matter. The standard model can't explain dark matter, but some SUSY particles could be perfect candidates. If the muon's wobble is caused by supersymmetric particles, the lightest one, like the neutralino, could make up the invisible matter holding galaxies together. But there's more. Some theories suggest a whole dark sector of particles and forces barely interacting with our own dark photons or dark Z bosons could be behind the muon's strange behavior. If true, the Muon-g2 experiment is giving us our first glimpse into this hidden world. The idea that one experiment could link quantum physics and cosmic mysteries is thrilling. The muon may be our messenger from the dark universe. Dark matter might not be completely silent. It could be whispering through the quantum world. The search for answers has never been more exciting. The Muon-g2 anomaly challenges the completeness of the standard model. It suggests there are new particles or forces waiting to be discovered. A fifth fundamental force with its own boson could be at play, something the standard model never predicted. Or perhaps new particles like superpartners or leptoquarks are crowding the quantum vacuum. The anomaly gives us our first clues about their properties, narrowing the search. Science advances by finding cracks in our best theories, and this is the biggest crack in 50 years. Any new theory must now explain the muon's anomalous magnetic moment. The search for new physics is no longer speculative. It's driven by hard data. The muon's wobble is transforming the quest for fundamental truth. We're on the verge of rewriting the rules of reality. One experiment isn't the end of the story, it's just the beginning. Fermilab will keep collecting data, sharpening the measurement of the muon's wobble. Theorists are refining their calculations, double-checking every detail. Meanwhile, a new experiment in Japan at JPAR will provide an independent test. If JPAR confirms the anomaly, the case for new physics will be undeniable. But to discover what's causing it, we need particle colliders. The Large Hadron Collider is already searching for the new particles hinted at by G2. Future colliders with even higher energies could produce these particles directly. The muon anomaly is a powerful reason to build the next generation of accelerators. The race to uncover new physics is accelerating. We started with a tiny wobble and found a giant mystery. The muon's strange dance is challenging our most fundamental ideas about reality. The G2 anomaly is a turning point, a message from the universe that our story isn't finished. It connects the quantum world to cosmic puzzles like dark matter. This could be the first sign of supersymmetry, a fifth force, or a hidden dark sector. Whatever the answer, the universe is richer and more complex than we imagined. This discovery reignites our spirit of exploration, pushing us to new frontiers. The era of the standard model is ending. A new era is beginning. The muon's wobble lights the path forward, and the next chapter is ours to write. The universe is still full of secrets, and we're just getting started.